Aloha, greetings from Hawaii. My name is Vernon Bird, and along with my friends Terry and Cindy Stratton, we're really excited to have the opportunity to share with you a tour of our aquaponics facility at the University of the Nations in Kona. Each of us three will contribute to this virtual tour. I'll give you the introduction and describe our systems, and then Cindy will describe our operation methods for plant production, and Terry's going to tell you about some of the innovations that we've been evaluating. Terry, Cindy, and I have been working together for the past 7 years here in Kona. Terry and Cindy are on the left, and I'm on the right here. We get to travel to other countries occasionally to talk and train about aquaponics, and here we were at an Eco Asia conference in Thailand last year. But today, we're going to show you around our facility, and we're going to tell you who we are, what we do, and why we do it. And as I said earlier, we'll also describe a few of the innovations that we're testing, and something like improved airlift pumps, for instance. So who are we? Well, the University of the Nations is the training arm of an international Christian youth movement called Youth with a Mission, and the acronym YWAM is often used. The university headquarters are in Lausanne, Switzerland, and their operating locations scattered around the globe. Our campus in Kona is one of the largest ones in the system, and we've got an international student body here. In the Science and Technology College of the university, we provide mostly hands-on training, in this case in aquaponics, and other areas of community technology related to food, energy, and water and sanitation. As part of our Natural Farm Training Center, aquaponics is one of the methods of sustainable agriculture that we demonstrate, test, and teach. Our aquaponics facility was started in 2009 with 4 deepwater culture rafts, patterned loosely after the University of Virgin Islands system. Original objectives were to evaluate the use of high levels of oxygenation in the water, and that was a device that was patented by the company that originally built our system. They wanted to test that in a place where there was year-round growing. Aquaponics is relatively popular in Hawaii because of the year-round growing season, and also in Hawaii there's a lack of well-developed soil in many areas because the landscape is dominated by historic and recent lava flows. Our climate on the west side here of the Big Island, you can see Kailua there where we're located, is really stable. The annual monthly average high and low temperatures are 85 degrees and 72 Fahrenheit. Summers are slightly warmer than the winters, and we do have a pronounced dry season in the winter on the west side of the island. Over the years, we've added different expressions of most of the primary types of aquaponics units to our system, besides the original 4 deepwater culture rafts. And we've added media beds, nutrient film technique, and aeroponics. And we're going to show you these today and tell you a little about our experiences in growing fish and plants outside and year-round in aquaponics. One of our objectives for our system is demonstration. And we get a fair number of visitors here, from school groups to professionals that are visiting from other countries that happen to be in Hawaii or came specifically to our university and want to know more about aquaponics. We have formal training, and that's really our primary objective as a university. And we use a combination of classroom and on-hands training. Our formal courses include a week-long workshop for students that just want to be exposed to this technology. And of course, we invite community members as well as our university students to those training sessions. We have a 2-week intensive training on aquaponics that is part of our upper level school called Stewardship and Sustainability. And then we offer quarter-long or sometimes longer internships for those really wanting to become proficient as builders and operators of aquaponics. And our staff and our students conduct outreaches, usually in a community development context in various countries, including recently Nepal, India, Thailand, and Bangladesh. We teach workshops, help build small teaching and trial aquaponics units, and some larger units, typically at places like children's homes or small training centers that want to become more sustainable and have aquaponics be a part of that. Occasionally, we get to network at conferences and also get to offer technical assistance, sometimes in the field. This unit on the bottom left here, Terry and Cindy are looking at the clarifier between the two fish tanks. That was built by the Fly Fishermen's Association from the United States. And it is at a Youth with a Mission operating location there in Kathmandu, Nepal, offering training and jobs for women who have been rescued out of trafficking situations. I think one of our members here of the association, Aaron Imhoff, was involved in designing that one. But you know, we do share some knowledge, but I think we learn more on our trips than we actually impart. Besides training and demonstration, we do produce, have an objective for production in our system, and the food that we produce goes to the campus cafeteria. The produce goes there, and the fish go to the homeless feeding program along with some of our produce, and we make fish available when we do a harvest to campus staff for a small donation. Now, we've grown a number of different plants in our aquaponics system over the last 10 years, but we've gradually refined our production to match the needs of the cafeteria. So currently, we're growing primarily leafy greens like arugula, lettuce, and kale, bunching onions, and herbs like basil and parsley. And our fish are primarily tilapia hybrids between Nile and Mozambique. But we also have raised Chinese catfish in systems with lower oxygen levels since they can breathe atmospheric oxygen. So I've told you a little bit about what we do, and now I want to describe our systems. These deep water culture rafts are part of the original 4 in the system. They're 48 feet long and 4 feet wide, but they're only about 7 inches deep, a little bit more shallow than is recommended. Since we grow mostly shallow-rooted plants, they've worked well in our situation. We also have media beds. They range from lined wooden boxes, like you see on the left here, and we have a little bit of hydroton that we use to illustrate in a couple of our media beds, but mostly we use cinder that's available locally. The blue barrels are so common around the world and available to build small or larger units from. And you can see here we have one small PVC tower that sort of illustrates that technology. And then we have available to us, and it's pretty common throughout the West, is these cement mixing trays. And this bed you see here includes 4 of those for small media beds. We have built several systems. This just is one of them, a small system that takes advantage of both media, the higher ones there, and deep water culture. And for small systems, for rafts, for deep water rafts, these media beds provide the biofiltration and physical filtration for systems that may not be big enough. That is, the deep raft might not be big enough themselves to have surface area sufficient for adequate bacteria populations for nitrification and mineralization. We haven't done a lot with the nutrient flow technique, but we do have it for demonstration and learning ourselves. And you can see we have both the commercial gutters and then PVC gutters, which is what we would use in developing countries. And we've got a couple of configurations of aeroponics, an A-frame and circular. And Terry's going to tell you more about aeroponics a little bit later. You don't need to there's more detail in this table probably than you're interested in, but just to say that we have 14 separate systems defined as grow beds with unique fish tanks or with unique designs like aeroponics that maybe share a tank with another grow bed. And as you can see, they vary from about a meter square, little guys of grow area, to our bigger deep rafts that are about 18 meters squared in surface area. And as I've described, we have examples of most of the main types of grow beds, and you can see them listed there. In total, we have about 100 meters squared of growing space. That's about 1,000 square feet. Now the fish tanks that we have about 12 of them. They range in the volume of water that we keep in them from about 2,500 gallons in that top center. That's a swimming pool. To as small as partial blue drum, about 30 gallons or 115 liters. But most of them are in the range of 100 to 500 gallons. We actually do design them with pumps that can pump the volume of the fish tank every 1 to 2 hours. Most of our systems have passive settling clarifiers, except for some of the smaller media beds where the media acts as both a solid filter and a biofilter. Our largest systems have additional physical filters like this box with Metalla filter pads to collect some of the solids remaining after the clarifiers. We use both external siphons and bell siphons in our media beds to circulate the water. Now, our plant stocking density is a little bit higher than I see in the literature that is more of an average for lettuce. We actually have about 50 plants per meter squared in our system. That's about 4.5 per foot squared. Our larger plants, of course, like basil and kale, are spaced further, and the spacing varies in media beds depending on what species is there. Fish stocking density and feeding rate ratios are as follows here. The tilapia are stocked at no more than 1 pound per 5 gallons of water. That's roughly a half kg per 20 liters. But most of our systems have lower stocking rates than that. They're on the order of maybe 1 pound per 8 to 10 gallons. And that we can do that because we're growing mostly leafy greens. And they are not as demanding on nutrients as our plants that are growing fruit. So we've adopted a feeding rate ratio of about 30 grams. And that's 30 grams of fish food per meter squared of grow bed surface per day. Our decision is based on reading a number of things, but Wilson Leonard's 2017 Commercial Aquaponics Systems book is so helpful in understanding some of the issues with feeding rate ratios. And because we have the leafy greens, and also we're beginning now to mineralize our waste back into the system, we feel that the lower feeding rate than, say, that recommended at the University of Virgin Islands works for us. Also, fish food is really expensive in Hawaii due to the shipping costs, so we want to be efficient with our resources. We try to control breeding for the tilapia because that can be a problem of overpopulating a tank. And we raise those fish in our breeding tanks to about 300 to 350 grams, or 250 to 350, in that ballpark. And then we'll stock them at that size because we are able to determine the sex more reliably manually at that size. And we're stocking tanks that are where we're harvesting all of the fish at one time. So we stock enough fish, we introduce enough fish so that they're getting about 3% of their body weight per day. That's the total biomass based on this 30 grams per meter squared per day. And then at harvest, the fish will be getting about 1% of their biomass because they've about tripled in size to this 1 kg harvest weight. Here's a summary of what we normally, over the last few years, have produced. Our annual harvest of leafy greens, and the majority of that is lettuce, is about 4,500 pounds per year in our system. And again, we don't try to maximize fish production, but we've been harvesting around 440 pounds, 200 kg a year at this, and I'm usually trying to grow them out to about a kg each. Well, that's sort of the description of our system. And now I want to turn it over to Cindy, who is going to tell you more about how we actually process, what the process is for our production. So you're Cindy.
Hello, I'm here to share about the aquaponics operations at the University of the Nations. We function with the goal of keeping things healthy, easy, and reproducible. Let's begin with harvest. We start by making tags for every raft or bed to be harvested. We wash scissors, bins, and hands. We harvest entire rafts comprising of single kinds of plant. We weigh the produce and the waste. We keep hard and digital copies for each raft, differentiating single or multiple harvest in our records. We label each bin and deliver to our cafeteria or to the local feeding program for them to process. And it's cleanup time, so in order to keep our systems happy, we separate organic material from rocks so that they can be reused. Our operations function with an always changing volunteer work crew. So we found we need some memorable processes. We call this rippy tippy tap tap swish. Here's the rip. There's the tip. And the tap 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 and the swish. To minimize water usage, we use a sifter to clean the bucket water of organic material. To clean rafts, we rinse, scrub, rinse, but only the raft tops, we leaving the biofilm on the bottom. Organic waste goes to the compost or to worms. The rocks are first rinsed, then sifted into 2 sizes. To stock the pots, we have larger rocks on the bottom, so they'll stay in the net pots without falling out. And then smaller rocks on top, which is easier for sprouting. This board is made from PVC pipe, and it's designed to get a measured amount of rocks in each pot. It's sized for the larger rocks we use in our net pots, and it's spaced to fit our trays. The big rocks are measured and delivered. We top off with small rocks by hand, adding dents in each pot for seed placement. We plant and cover. We use both pelleted seeds and not. Each tray is labeled and soaked. Then to the seedling table where they get automatically watered with city water. After about 5 to 8 days, we move the seedlings to the nutrient-rich nursery. Then we transfer the older, bigger starts and place them in rafts, single type, same age per raft. As our rafts wear out, we use plastic spacers to hold up the pots. We label and enter each raft in the record book. And the rafts, of course, slide up as weeks progress and harvest allows. In aeroponics, we use coconut coir because it's lighter and it can be recycled to our compost after every use. Media beds are about the same process, but of course, without the pots. We plant in rows or we broadcast in the media. When harvesting, be sure to get the roots. We feed the fish 2 times a day, and this allows for daily monitoring of water levels, fish health, and the pumps. We schedule routine checks for pests on the plants and under. Oh no, it's time to go fishing. Water chemistry is taken weekly. Calcium carbonate and iron chelate are added as needed. Pumps, clarifies, filters, and beds are on a regular cleaning schedule. We live in growing zone 11A, so we use shade cloth as our bird net, but we have additional adjustable shade as needed. Fish management is a whole other subject. We keep them healthy. We do some breeding, and we harvest for our community. Thank you.
Hi, this is Terry. For the final part of the farm tour, we wanted to share with you some of the innovative things that have proven valuable to us. These are things that have upgraded the reliability and cost effectiveness of our system. Well, we can't discuss innovations at U of N Kona without giving credit to our friend Glenn Martinez. In the last few years, we've enjoyed getting to know Glenn, who along with business manager Natalie Cash run a beautiful aquaponics and permaculture operation called Olamana Gardens on the nearby island of Oahu. Glenn has donated a lot of teaching, consultation time, and equipment to our university. His innovations and instruction have generated tons of interest from students and visitors. For one thing, we've been teaching and using airlift pumps that Glenn designed. They've been working great for us for over 5 years. By definition, an airlift pump uses air bubbles to lift water. Until recently, 10 to 15 centimeters was about as high as airlift pumps could lift. Glenn has several airlift designs that can easily lift water 1 to 4 meters at a rate of about 400 to 2,000 liters of water per hour. His pumps can also be configured to pump water much higher. Most of our airlifts are powered by small, energy-saving diaphragm-style air compressors, ranging from 35 to 110 watts in size. Here's what we found out about airlift pumps. For one thing, they're very resistant to blockage or fouling. They can pass most gravel, weeds, small fish, and sludge right through the pump without blocking or damage. Unlike conventional water pumps, airlift pumps are not affected by sand or other abrasive materials in the water. They're also unaffected by water level and will not burn out if the water level drops below the pump intake because they're air-cooled, not water-cooled. We found them to be more reliable, longer lasting, and less costly to maintain. Airlift pumps also aerate the water as they lift it, providing dissolved oxygen for fish, plants, and nitrifying bacteria. This feature can cut down on the amount of additional aeration needed for a system. Another cost-saving benefit of airlift pumps stems from the fact that many air compressors have a long life, and unlike many conventional water pumps, are easy and relatively inexpensive to repair. We've also saved money on electric bills with these pumps. Here's a 30-watt air compressor running a system. We also have replaced a 220-watt submersible pump with an 80-watt airlift, saving us about $400 a year on electricity on this one pump. For security or convenience, the air compressor can be placed far away from the water tank. This provides a safety advantage because there doesn't need to be an electrical pump in or an electrical connection near the water, and the air compressor can be locked up in a secure location. One of Glenn's designs is the pipe-in-a-pipe airlift. It's an ingenious and easy-to-build pump using off-the-shelf PVC parts. It can be scaled and custom-made to fit many applications. Here's another example of one we're using to supply water to the clarifier that overflows into one of our 14-meter-long deep-water culture systems. The well for the airlift tees into the covered IBC that is the fish tank. Here's another example during construction. In many locations, all you need is a post hole digger, but our location has gravel fill over lava rock. These pumps have generated quite a bit of interest when we've taught about them and made them during community development projects or seminars in Thailand, India, Bangladesh, and Nepal. Another one of Glenn's discoveries, as he likes to call them, is the burper pump. A burper-style airlift uses a one-way check valve, PVC pipe and fittings, and an air compressor to lift and move water. This brass check valve is overkill. We have inexpensive PVC check valves that have worked for years. It is less efficient at lifting water compared to the pipe-in-a-pipe pump, but is completely adequate for many applications. Along with all the other airlift pump advantages, it can be used where you can't or don't want to dig a hole. As you can see in this picture, the burper pump can be configured into a shape that fits into a small tank, so it's a very versatile design. Next, we'll take a look at high output, low start volume siphons. Siphons, as you know, on flood and drain media beds can be a challenge. It's hard to get them to start reliably when the output of your pump is less than ideal. We had several applications where we wanted the grow bed or tank to drain rapidly. This required a large diameter, like 2-inch siphon outlet. Normally, a large siphon needs substantial water flow to start. Just a trickle of water through a conventional large siphon won't create conditions for it to start. Glenn showed us several solutions to that problem. The double 45-degree fitting turned to a 45-degree angle creates a trap that lets water and air out, but keeps air from returning back into the siphon to equalize the air pressure. So a low pressure condition is created in the siphon that draws water from the tank and starts the siphon more reliably. The cup outlet is another design that we've had good success with. This is another air trap that is simple to construct using a PVC cap. You'll see in a minute how we used it in our new flood and drain plant nursery. Our goal with that was to increase our deep water culture crop production by 25% by growing larger, healthier plant starts before we place them in the main raft grow beds. In reality, our old seedling nursery was falling apart and was too small, so this was a needed upgrade. In this design, trays of plants are supported up off the grow bed floor on PVC support frames designed to allow the trays to slide the length of the frames. Periodically, 100 gallons of water floods up out of the floor of the grow bed and raises the water level to soak the net pots. This flooding action is accomplished through the high output, low start volume cup siphon described earlier. That siphon floods into a container that catches the water and pipes it to the grow bed. It takes about 2 minutes to flood the grow bed with 100 gallons or 380 liters of water, raising the water level to soak the plant starts. Then another Glenn Martinez innovation passively sets the high water limit. When that top level is reached and the siphoning stops, the water level drains through notches in the standpipe back down to the bottom of the net pots. These dialomatic standpipes let us control the depth and rate of drainage. The benefits of this system include excellent circulation of nutrient and oxygen-rich water throughout a densely packed grow bed that holds 2,200 plants. It eliminates stagnant zones in the grow bed and in individual net pots, because each pot drains completely before being reflooded with fresh water. Half of the volume of the grow bed is exchanged every 35 minutes. Oxygen availability to the plant roots and to beneficial biology is optimized because of alternating exposure to atmospheric oxygen and the oxygen-rich water. Okay, let's move on to an overview of low-pressure aeroponics for vertical grow beds. Another Martinez innovation that we've used to grow about 220 plants in a little over 2.5 square meter footprint. Normally, aeroponics uses high-pressure fine mist sprayers and filtered hydroponic solution. That kind of setup would constantly have blockage problems in your typical aquaponics system. Glenn's design uses a spiral sprayer made originally for high-output overhead fire suppression systems. When the right balance of air and water are pumped through one of these spiral sprayers by an airlift pump, the result is a sprayer that can pass unfiltered aquaponics water without blocking. One easy-to-build expression of this is the A-frame model. It consists of a lined plywood and 2x4 collection pan, PVC frame, and styrofoam insulation panels. Inside are a couple of spiral sprayers atop a double outlet airlift pump. This arrangement has grow beds on both sides that effectively double the number of plants per given area compared to our horizontal grow bed. Rotating circular aeroponics is another Glenn Martinez prototype we're experimenting with. We've had good results growing lettuce, herbs, and bunching onions. There is just one spiral sprayer atop a modified airlift pump in the middle of the cone. The fish are in the blue barrel. Since the grow bed is on a floating raft, it can be configured to rotate by a water jet. One final innovation of Glenn's that we'd like to share with you is the Dragontail aerator. This is a PVC pipe configuration that increases the aerating effect of falling water, resulting in higher dissolved oxygen in the water. Because the pipe is arranged in cascading loops, he calls it a Dragontail. The opposing forces of downward water current and the upward movement of bubbles in water are at work in these passive aerators. The bubbles are suspended in the water column, and as the water deepens, the air bubbles are compressed at depth. They spend more time in contact with the water compared to water being sprayed on the surface. Well, that's it for the tour. Thanks for your interest.